The aim of this video is to guide you through the setup of an added resistance in wave simulation which uses a motion carriage approach. In this method we simulate the vessel moving forward at a constant ship speed and allow it to pitch and heave freely. The common method for this kind of application usually involves us specifying the ship velocity within the wave definition. For a linear first order wave, the ship velocity is present in the current and wind inputs, whereas for a fifth order Stokes wave, the velocity is included in the additional velocity field. The reason for this is that the current is fed into the wave definition for a fifth order wave specified with a wave period. There are limitations with this approach for a couple of reasons. The first is when simulating a vessel in a following sea, as the vessel velocity is superposed on top of the wave velocity for both the first and fifth order waves. This superposition model is not fully valid when the wave is propagating in the same direction as the ship, as for a static vessel the velocity components of the additional velocity and wave velocity would be opposing each other. The second is that the additional velocity for a fifth order wave purely superposes this additional velocity on top of the computed theoretical wave velocity. It is a simplistic model and useful for small ship velocities when compared to the wave velocity itself. It is still valid at higher ship velocities, however the higher the ship velocity when compared to the wave velocity, the more error is likely to be present due to the superposition. An alternative approach we can use is to simulate the forward surge motion of the vessel whilst having the boundary conditions set to those of the wave we are modelling without the need for an additional or superposed velocity. This is a similar methodology to one of the two main options for simulating self-propulsion, in which the vessel is free to surge. To demonstrate this setup, we will start from a typical first order added resistance in wave simulation consisting of two regions with an overset mesh approach. The background region remains fixed and we apply the relevant boundary conditions, whilst the overset region contains the hull with the motion specification set to DFBI rotation and translation. For this application, the motion normally has the pitch and heave degrees of freedom active. The key difference for the motion carriage approach is the specification of the surge motion in the x direction. As we have two regions present, the surge motion needs to be incorporated within each region to ensure that the overset region remains in the same position in the x-axis with respect to the background region. First, we will make the necessary changes to the overset region controlled by the DFBI rotation translation motion. The first step is to change the body motion option from free motion to planar motion carriage, which creates a new planar motion carriage node. Following this, we can change the planar motion option to planar motion mechanism, as this allows for a direct input of surge velocity. Added resistance simulation with either a following or head wave, we need just to enable the free heave and free pitch within the planar motion carriage properties. Within the planar motion mechanism properties, we only need to specify the x velocity as the required surge speed. This velocity should be input in the direction in which the ship is travelling and will be the same value that was included in the additional velocity field with the standard approach. The final change which needs to be made is the attachment point. This would most likely be known through experimental data for any true PMM case, but for this particular application, as there isn't a physical attachment, we can just set this to be equal to the C of G. It should be noted that when using the planar motion mechanism, the body local coordinate system origin of the DFBI body is located at the attachment point and not at the centre of gravity. At this point, the overset region setup is complete and we can move on to the background region. For this, we will need to create a new translation motion with the translation x velocity set to be the required value used in the planar motion input. We can then assign this motion to the background region motion specification. The motion related setup is now complete. The next step is to go back into the wave properties and remove the velocity components included for the air and current. This will be the additional velocity component for a fifth order wave. We will now run the simulation to visualize the vessel moving in the surge axis and discuss the post-processing in the meantime. To assist with post-processing, we can also create a managed coordinate system to ensure that any scenes can follow the motion we prescribe. To do this, we need to create a new local Cartesian coordinate system with its origin at the initial attachment point or CFG of the boat. We can then go back to the translation motion and select this coordinate system in the Manage Coordinate System options. If we then navigate to a scene, we can alter the view to be in this moving coordinate system. The reason that we don't select the body coordinate system of the DFBI body is that we only want the camera to follow the X translation and not the heave and pitch of the vessel, as would be present with the DFBI body coordinate system. As we can see, both regions are translating from their original position indicated by the outline. This video has demonstrated an approach for setting up a motion carriage style simulation and also specified instances in which it may be beneficial to use this approach. In this approach, a following wave was demonstrated. For this particular case, it is recommended to change the usual pressure outlet boundary aft of the ship to a velocity inlet.